Okay, so for this tool that I'm going to present is very much at the stage of the idea, which means that this event is particularly useful to us to get as many comments and suggestions from you. And yeah, so as I said, I'm Emmanuel Rouges. It's in collaboration with Ted Shepard and also with Marianne Kretschmer, who's also here. And oops. So you are probably most of you aware of the concept of weather regime, so I'll keep this introduction quite short. So there are large-scale circulation patterns which represent more constructed using a clustering algorithm, which uses as input the 500 hectopascal geopotential height. The most well-known and which was originally created uses four regimes, which are presented here with NAO+, NAO negative, blocking regime, and the Atlantic ridge. There are also other regime classifications which are suggested, which are supposed to include more of the year-round variability, so using 6 to 7 regimes, for example. So one of the interests about weather regimes is due to their large scale and persistence, they can be used to forecast at longer time scales, such as subseasonal time scale. And this is why now weather centers, such as ECMWF, are producing products such as this one, looking at the weather regime frequency. And also weather regimes can be used directly to construct a forecast. So here in this example, I'm looking at a week 2 forecast for an energy variable, and you see here the scale for a grid point forecast, and here different kind of weather regimes. And you see that using the weather regimes, the scale is slightly better. So one of the main interests for weather regimes is really that they are modulating surface weather, sometimes leading to very extreme conditions such as cold spells or heat waves. Also, they're impacting the energy-related variables such as wind, solar radiation, or temperature. So the motivation very much for this tool was looking at the coldest winter for Europe in the 20th century, which had a very persisting NAO negative. As you can see here, we have very cold conditions during the December to February period. And here the frequency of the NAO negative is very high compared to other regimes, in particular during the February months where more than half of the days were NAO negative. So this essentially triggers the question of what would happen if you constrain the winter weather conditions using weather regimes. So the idea here is that we have 40 years of energy data, so model energy data from energy demand to wind and solar generation. And here we want to set the regime frequency or proportion of regimes across a particular winter, potentially also influence the persistence of them. And then we can extract all the days that corresponding to our criteria. And also, as we have 40 years of data, potentially create permutation, which means that we have an ensemble, I would say, of scenarios. Then you can extract the corresponding energy data, and the output would enable to analyze energy extremes. So looking both at the energy, the frequency of extremes, intensity, and persistence. And as we have an ensemble of scenarios, it's then possible to identify worst case scenarios. And then, if interesting, it's then possible to backtrack and then determine which weather regime sequence or which weather conditions were responsible for this worst case scenario. So really the idea here is to leverage the information that we can have from weather regimes, So their impact on surface conditions, in particular on energy-related variables. The knowledge that persisting regimes can lead to extreme cold conditions and significantly impact the energy sector. So really the idea of this tool is to explore potential worst-case scenarios from the perspective of the energy sector across Europe. And I'm welcome to answer any questions. And as I said, maybe at the start, where any comments, suggestions are welcome.